Hello guys, so in this video, I'm gonna do examples 7 and 8, and we're gonna discuss different types of solutions that a system and 3 equations may have. So let's start with example 7. I'm gonna use the usual 5 steps for solving the systems in 3 equations in 3 variables. By the way, you need as many equations as you have variables in order for the system to have a unique solution. So if you have 3 variables, 3 equations is necessary. More is okay, but less is not. So, all right. What I'm going to do, I'm going to multiply my first equation by 2. So I'm going to have 4x plus 2y minus 6z equals 0. Okay, next equation. I had to multiply by -2, actually, not +2. Well, I can multiply the second equation by -1. That's okay. So I'm going to have -4x minus 2y plus 6z equals 0. And when I combine these two equations, what happens? All of the variables canceling out, and I have 0 equals 0. So all of the variables dropped out. So at this point, I don't have to continue solving this equation or this system. So what we got is a true statement. And statement that's always true is also known as an identity. And this tells us that we're looking at a dependent system. Okay, now we know that the system has infinitely many solutions. The question now is, how do we write the answer to this system? Remember that we said earlier that what can happen with linear equations, they could either cross at one point, or they could be parallel to each other, or they could coincide. And this is where we get our when they coincide, we get our dependent system, and when they are parallel and don't cross at all, we have inconsistent system with no solutions. Now, what kind of situations can we run into with the three-dimensional equation? So here, since we have 3 variables x, y, z, that represents a 3-dimensional space. And each of these equations, they represent actually planes instead of just lines. So let's see what happens. So here in this slide, you see the case of inconsistent system. That's the system that has no solutions. How can that happen? Well, we could have 3 planes that are parallel to each other and they never intersect, but this is not the only way. We could have 2 parallel planes and one plane that cuts through both of them. So these planes never cross, these two. So there is no common intersection for those planes. Now, or planes could cross like this. So any pair of the planes, they do have a common line, but there is no common point for all of these 3 planes. So they will not never cross all 3 of them together. So in any one of these situations, you're going to have an inconsistent system. But what about dependent system? This slide actually represents a dependent system. Oops, I misspelled the word. Okay, so this is a consistent system is when you have three planes that intersect. None of them are parallel to each other. And they intersect in only one point, and that's what we usually find. We find that coordinates of that one point when we solve a system in three equations. Occasionally, the all three planes are going to intersect on a line instead of a point. And in this case, we're going to have a dependent system, which has a solution, but the solution is actually a line in space, so quite complex. The question is, how do you express that line? How do you write that line in space as a solution to the system? So let's see. So basically, you're looking for the ways to express y and z in terms of x. And then you let x be anything, and then you will figure out y and z in terms of x. Once you know the x, you can figure them out. So the first way of doing that is to look for how can we eliminate y first. So, and I see that if I add the first equation and the third equation, then the y's will be canceled out. So I'm going to do that. So the first one is 2x plus y minus 3z's equals 0. And the third is x minus y plus z equals 0. Okay, so I have 3x, y is gone, and negative 3z's and z is negative 2z's equals 0. So now I'm going to solve it for z. Negative 2z equals negative 3x. So z is negative 3/2 x. Okay, so now I have expression of z in terms of x. Now I'm going to do the same for y. So in order to solve for y, I need to eliminate z, right? I need something that will give me only x and y. So here, again, I have negative 3z, and I could multiply by negative 2 to match it with to get a 6 there, to match it with negative 6. Or I could multiply the third equation by positive 3, and again, match it up with 1. We could choose the same equations for that operation as well. So I'm again going to be, well, let's choose 1 and 2 for just for the sake of it. And so I'm multiplying the first equation by negative 2. So again, I have negative 4x minus 2y plus 6x equals 0. And then positive 4x. Oh, we just did that in 1 and 2, right? And everything canceled out. So let's stick with 1 and 3, or we could do 2 and 3. So these guys are parallel. Okay, so 4x plus 2y minus 6z equals 0. And I'm multiplying this equation by 6. So I have 6x minus 6y minus plus 6z equals 0. So I will have, okay, 10 x minus 4y equals 0. So y, I'm gonna go here. Okay, negative 4y equals negative 10x. So y equals 10 over 4x. So y is 5 halves x. And this is my expression for y. And so when I write my solution, so I'm going to write x could be anything, so just leave it as x. But once you specify the x, you can figure out the y by doing this. 5 half x for y. And how do you figure out z? By doing this. Negative 3 halves x. So that's how you write the equation of that line in space. So this slide right here, it represents the solution to that system of equation that we just worked on. And as you can see, there's two planes that are actually, they coincide. It's the same plane. And there is another plane that cuts that plane, those two planes actually on one line. So these two planes, they have infinitely many common points, but when you consider the third plane, there's only a line of that represents the set of the solution set.